Space weather refers to the environmental conditions in space, primarily influenced by the sun's activity, that can have significant effects on technology, infrastructure, and human activities both in space and on Earth. Space weather phenomena include solar flares, coronal mass ejections, CMEs, solar wind, geomagnetic storms, and cosmic rays. Monitoring solar activity and space weather is crucial for understanding and mitigating potential impacts on Earth's magnetosphere, ionosphere, telecommunications systems, power grids, satellite operations, and astronaut safety. To monitor solar activity and space weather, scientists and researchers employ a variety of ground-based and space-based instruments, as well as computational models and data analysis techniques. Some of the key methods and technologies used to monitor solar activity and space weather include solar observatories. Ground-based and space-based solar observatories, such as the Solar Dynamics Observatory, SDO, the Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe, continuously monitor the Sun's surface, atmosphere, and magnetic field to track solar flares, CMEs, sunspots, and other solar phenomena. These observatories use telescopes, spectrographs, and other instruments to capture high-resolution images and data of the Sun's activity in various wavelengths of light. Solar imagers. Solar imagers, such as the Helioseismic and Magnetic Imager, HMI, on the Solar Dynamics Observatory, SDO, provide real-time images and data of the Sun's surface and magnetic field, allowing scientists to monitor sunspot formation, solar flares, and solar eruptions. Solar imagers use optical and magnetic sensors to detect changes in solar activity and track the evolution of solar phenomena over time. Solar flares and CME detectors. Detectors and instruments onboard satellites and spacecraft, such as the Geostationary Operational Environmental Satellites, GOES, and the Advanced Composition Explorer, ACE, monitor solar flares and CMEs as they propagate through space towards Earth. These detectors measure high-energy particles, electromagnetic radiation, and magnetic fields associated with solar eruptions, providing early warning of potential impacts on Earth's magnetosphere and ionosphere. Magnetometers. Ground-based and satellite-based magnetometers measure changes in Earth's magnetic field caused by solar wind, geomagnetic storms, and magnetic disturbances associated with solar activity. Magnetometers provide valuable data for monitoring space weather conditions and assessing their potential effects on power grids, telecommunications systems, and navigation systems. Ionospheric monitors. Ground-based and satellite-based ionospheric monitors measure changes in Earth's ionosphere caused by solar radiation, solar flares, and geomagnetic storms. These monitors use radio waves, GPS signals, and other techniques to monitor ionospheric density, electron content, and propagation characteristics, providing critical information for predicting and mitigating disruptions to radio communications, GPS navigation, and satellite operations. Computational models. Computational models and simulations are used to predict and forecast space weather conditions based on observations of solar activity, solar wind parameters, and geomagnetic indices. Numerical models, such as the Space Weather Modeling Framework, SWMF, and the Community Coordinated Modeling Center, CCMC, simulate the dynamics of the Sun-Earth system and predict the arrival and intensity of solar storms, geomagnetic disturbances, and ionospheric anomalies. By combining data from various monitoring systems, observational platforms, and computational models, scientists and space weather forecasters can track solar activity, predict space weather conditions, and provide warnings and alerts to mitigate potential impacts on Earth's technology and infrastructure. Space weather monitoring plays a critical role in safeguarding satellite operations, protecting astronauts in space, preserving critical infrastructure, and ensuring the reliability and resilience of telecommunications, navigation, and power systems in the face of solar disturbances and geomagnetic storms.